In the chapter on probabilistic robotics, what we have seen thus far is basically the math under the assumption that robots live in the ideal world where they have perfect sensors and perfect actuators. Unfortunately, there's no such world, and at least not in the real world that we live in. And robots are rather faced with imperfect sensors and imperfect actuators. And this is what we are going to discuss today, how we can actually deal with that. And this is kind of like the core chapter of this course. That's what we are going to discuss today. And the goal will be today and on Friday basically derive the basic underlying equation for perception and state estimation in robotics. This is actually what is called probabilistic robotics. There's been no exam thus far where the equation and the understanding of that equation was not asked. Right? Just to give you an intuition about the importance of that equation, although it's also sometimes obviously misunderstood that this is also not the only equation that is going to be asked in exams. But what you can be assured is that this equation will be asked. Right? It's a relatively long equation, and the derivation will take approximately 1 hour. But in the end, the equation is relatively modular. It has 4 components, and all these components need to be understood and known, and that's what we are going to discuss today, how to actually arrive at that equation. And then the next weeks we will basically spend with implementing this equation and basically answering the question of how can we realize this on a real robot to arrive at a robust navigation behavior, for example. And we will also implement this equation in different forms, in different ways, for example, for building maps of the environment, for figuring out where the robot is, given a map, and then we will also discuss the application of this equation for the case where the robot does both at the same time, building a map and figuring out where it is in the environment. So this is a relatively important part of that chapter, and also if we take our time and we will derive this from first principles. Often all these equations look like magically appearing, but what we will do is we will basically start with the key concepts of probabilistic reasoning, the axioms. We will start with the axioms and from those derive that equation. So the key idea of probabilistic robotics is basically, given the fact that robots live in a world, in an imperfect world, no perfect sensors, no perfect actuators, that we are trying to arrive at an explicit representation of uncertainty, which then allows us to reason about the uncertainty and which enables robot to do amazing things, like, for example, doing something like active perception, right, to reduce, for example, the uncertainty in their belief about their own state or the state of the environment. And also maybe perform actions that have minimum risk given the uncertainty that the robot actually currently has. And there are 2 concepts typically used in this context, which is perception. This is state estimation, and the equation that we are going to derive is the state estimation equation that we are going to use, and that is underlying many state estimation processes in real world. But also it forms the basis for that what we call utility optimization, because in principle, like, you do not have something like a given state, right? The system actually doesn't know in which state it or the environment is, so it needs to calculate actions under uncertainty, and this is something where this concept of utility optimization kicks in. This is also something that we will study in the AI course, so there is some overlap here. The AI course that will appear relatively at the end in couple of weeks from now, I think 2 to 3 weeks before the end of the term. We will also get to this relatively late, and might be at the very, very same time that we describe how this can actually be done, be implemented, like action generation based on uncertainty. But In order to do this, what we need to do first is figure out how we can represent uncertainty and deal with the uncertainty in the measurement processes and also in the execution processes in order to obtain that what we call a probabilistic belief about the state of the system. And the system can be either the robot itself, where it is, or the environment. So what is the state of the environment? I told you that we're going to start with the basic principles. So you basically look at the axioms of probability theory, which are depicted here. Right? These are 4 axioms, basically, that basically tell that all probabilities lie between 0 and 1. Right? Then probabilities are expressed over so-called expressions, which we typically call, denote as A or B, sometimes use different letters as well. And I must admit that we are not entirely consistent in this presentation, but take this as the opportunity to actually also train your brain and establish associations between slightly inconsistent formulations. Now you will also, when you look at textbooks, and there will also be slightly different formulations and uses of capital and lower case letters for P and so on and so forth. Sometimes I admit it's slightly mixed up, apologize, but at the same time it also introduces the need for some flexibility. So what we see is that probabilities need to lie between 0 and 1. It's amazing that people actually tend to forget this, and even in scientific papers there are papers that contain a sentence like, in this case we have assigned the probability -1, right, to whatsoever. That actually doesn't exist, and you will also get a little bit discussion about the fact that systems that use concepts deviating from these 4 axioms over here, there's actually a very nice proof from an Italian mathematician that they in the long run perform suboptimally. And which means that it's a good advice to actually use calculi that are actually compliant with these 4 axioms. And if this statement A that we have is exactly the statement true, so the constant true, which is a true statement, right, then we assign the value 1 to it, and if the statement is exactly false, then we assign the probability 0 to it. And then there's this 4th axiom, which in the very first place looks a little bit complicated, but it somehow combines the basic operators in probability theory or in logic, where we do have like the disjunction of 2 statements, A or B, and the conjunction of 2 statements, A and B. Right? And we combine this with somehow the arithmetic operations that we use for dealing with numbers. Right? And it basically says the probability of A or B is the probability of A plus the probability of B minus the probability of P of A, of the probability of A and B. Right? And also, like in the literature, some people drop this last term over here, and it turns out that this is a mistake. In general, all you need to know is that probabilities, they appear sometimes as a little bit magic. They are nothing else but counting. We are basically doing nothing else but counting how often things appear. And you can look at this, for example, when you look at axiom 3, and if you come up with this very, very simplistic counting argument, then you can easily see that there is an intuition behind this subtraction of this term P of A and B over here. So if you look at this figure, for example, so let's assume that this is our domain over here. And what we basically do is we group the things in this. We rearrange the objects in this domain, or in the way that basically we see here all cases in blue where A is true, like all objects for which A is true. And the probability that A is true then is basically nothing else but the size of this disk. And in addition, we group these objects for which B is true also in kind of like disk-like form, and they in this case have the very, very same size, but it actually doesn't matter that they have it even if this is distinct. And we also arrange those where A and B is true, for which A and B is true in a way that we have this overlapping area, just by rearrangement. Right? So what you can basically see is that the size of the blue disk relative to the domain is a probability that when you pick a random object that A is true, right? Which basically is P of A in that domain. Right? And the size of the yellow disk is the number of cases, right, where B is true. Right? And we now look at the expression P of A or B. Right? These are basically all the objects for which either the expression A or the expression B is true, which is nothing else but the area covered by the two circles. Right? But which is, this area, unfortunately, is less than the sum of the two areas of the individual circles. Because if you if you consider this, right, what you do is when they have an overlap, then it turns out that if you sum up the two individual sizes of the disks, which would be P of A plus P of B, right, then in this case you would count the overlapping area twice. Right? Which means that you have to, in order to come up with the correct value, you need to subtract the overlapping area once. Right? And this is why the disjunction of the two, A or B, is basically the size of A, size of B, minus the overlapping area. And of course, if the overlapping area is 0, which means there's no object for which A and B is true, then you can drop this term, because it's 0 then. And which, on the other hand, means that the two disks are disjoint and don't have an overlap. So this is basically the intuition behind this. And then people also often argue, but there is this equation which basically says that P of not A, right, which is the rest of the domain, is 1 minus P of A. Obviously, it's all the other objects in this domain. Right? So why is this not contained in the axioms? Mathematicians and also statisticians are like idealists. They actually want to have the minimum description that is sufficient to express everything that you need to say about what a theory. And this is why the axioms are typically a minimum set of axioms that make sure that you can actually derive everything else from those axioms. And this famous statement that P of A is 1 minus P of not A is basically can easily be derived from those 4 axioms that we saw before. Right? And all we need to do is we need all the axioms that we have seen thus far. So we start with P of A or non-A. Right? And from that we know that this is P of A plus P of non-A plus 1 minus P of A and non-A. Yeah, this is basically nothing else but text replacement. So we will throughout this course, we will very, very often do nothing else but text replacement. So if you think this is a super complex equation, all you need to do in this case is textually replace B by not A. And obviously, the very same thing should hold then. Right? Replacing this by not A, P of A or not A, P of A plus P of not A, minus P of A and not A. We will very often do this, just replacing text. So you can actually also ask maybe every child that can write and read letters, right, and has no clue about statistics, right, can do this text replacement. Right? And this is something that we're going to do very, very often. Right? And it's, in many cases, it's nothing else but just replacing text, no magic. Right? It's mechanically, even a computer could do this, that has no intuition about all this. Basically, we do have P of A or not A is this equation over here, just text replacement. And we know in logic, A or not A is always true. This is true. And we also know that A and not A is always false. There's no model for those expressions in propositional logic. And we know that P of true is one axiom, and we know that P of false is 0, the other axiom. And from that we get 1 is P of A plus P of non-A, and by simple rearrangement we get P of A is 1 minus P of non-A. Of course you could add this to the axioms, but why doing so if you can have a more compressed description of that what you need for probability theory. And basically everything else can be derived from that. Those axioms, all you need And what we will also do is we will basically introduce some terms and make some definitions from which we then play around with. Right? So what this is all we do. We basically use definitions in the remaining of this, and then apply these axioms, and also reason about some of these type of terms that we introduce by the definitions. Usually, like these constants that we use, like x or a, like denote that what we call a random variable. And in the case that a is an expression saying like there's going to be rain today whatsoever, it's probably false for today, fortunately. But in this case, we basically say this is a binary variable. The statement can be either true or false. But in general, we can also have continuous variables. For example, if you think about robot localization, you want to know where the robot is, then this x would be, if the robot lives on a plane, a three-dimensional vector which has like the component x coordinate, y coordinate, and orientation. Yeah. But it could also be that a variable that denotes in which room the robot might be, right? And in this area down here in the ground floor of this hall, this might be, I don't know exactly, I think 6 rooms are here, right? So x would be a 6-valued variable. It could be the hallway, this room, the next room, third room, or one of the 2 lecture halls. Of course, if you count additionally at the bathroom, then it's going to be 7, 8, 9, whatsoever, right? You name it. But then you would have like a more higher valued, but still discrete variable. And if you go to the domain of positions, then it's going to be a continuous variable, a 3-dimensional variable, for example, even. And then what you basically, the normal way of writing this down is if p of x equals small x, it's basically the probability that this variable has a specific value. Formally, we would have to write down like the probability that the sentence, today it's going to be raining, is true, equals true. But we are often make an abbreviation and simply write down this atomic value, and when we say it's going to be raining today, and this is our atomic value. So this is basically the probability that the variable x takes on value xi. Usually we say this p of something is a probability mass function. If we want to know what the probabilities are for the robot being in a specific room, then this could be one instance of that probability mass function. And in case it's a binary variable, like we only need to specify one value, the other one is directly given by the fact that over the domain that we have, over all values that the robot could actually obtain, the sum of those quantities in discrete case sums up to 1. And if I'm not wrong, this is the case also in here. So there we have like 4 rooms in this case, and overall the probability the robot must be anywhere in any of these 4 rooms. In the case this is a continuous variable, right, then things are not that easy anymore, because for any, because it's a dense domain, floating point numbers, it's no longer discrete, which means that the probability that the robot is at a specific location, 0, 0, and 0, is virtually 0, because it's impossible to exactly achieve a certain coordinate. And this is why you can actually only reason about the robot being in a certain interval, which is then calculated as the area under that probability mass function that you obtain by integrating over from a to b over p of x. So this is basically integrating over one of those functions, for example. So in general, we decide between discrete and continuous cases. Robot localization, for example, is a continuous problem, but we will also see discrete problems, and we can also turn this robot localization problem into a discrete problem by simply discretizing the number of positions the robot could be at, and not thinking of this as being a continuous valued function, but rather discrete function. We will see examples for that also throughout this course. Right? But the constraint is that over all cases of x, the sum of all p of x must be 1, and for the continuous case, meaning the area under that function must be 1. Then there's this so-called joint probabilities that we formulate as, for example, in this case, this conjunction that we saw before, that in this case in a multi-valued variables, this would be something like p of x equals x and y equals small y. Then we typically write this down as p of x comma y, meaning p of x and y. In the case that x doesn't tell us anything about y, meaning that those two disks that we have seen before are basically disjoint, then this turns out to be exactly the probability of p of x times the probability of y. Right, so this is so then they are basically independent. And this concept of being independent is defined as the following. Basically, we write down, or dependency is like p of x given y. This is something that, or this is basically a definition now. We write them whenever we write something like p of x given y, that basically stands for the case where we are interested in the probability of x given we exactly know that y is true. So we basically assume that we got the information about y, and we now want to know what is the probability of x being true given we have the evidence y. So for example, it could be the case that we are interested in the probability that it is raining outside given we have seen someone walking with an umbrella out there. Right, so the which is typically then different from the probability that and it's raining outside. Right? So which means that this expresses somehow the dependency of x from y, and this is basically mathematically, this is defined as p of x given y is p of x and y divided by p of y. There's nothing else but this definition. Right? On the other hand, you can just like multiply this equation by p of y, which is nicer because p of y could also be 0. Right? And we have p of x and y is p of x given y times p of y. Right? So this is basically a definition of the conditional probability. And obviously, if x and y are independent, meaning that y, the information of y doesn't tell us anything about x, that basically means that p of x given y equals p of x. Right? So for example, if you want to know as to whether it's raining today and you look into the webcam and you see bad weather in Freiburg downtown, or you use the Feldberg webcam and you see that it's raining out there, then maybe there's a higher chance that it's raining here in Freiburg, downtown Freiburg, compared to the information where you see actually nice weather over there. Right? So which means that somehow this information, it's raining on Feldberg, provides you with some more evidence about how the weather might be in Freiburg. However, if y is the information about how's the weather in Beijing, right, then this probably doesn't provide you with any information about how the weather in Freiburg is. I do not know whether there's any dependency between the weather in Beijing and Freiburg, but I doubt that there is. Right? And it could even be so small that actually information about the weather in Beijing does not change the probability of being sunshine in Freiburg, at least to any measure to any probability that we could measure. So in that case, you would argue that those two variables are independent. So the weather in China doesn't provide you with any information about the weather in Freiburg. So there's one law that we are going to use throughout this, which is called the law of total probability. And this is basically that in the discrete case, that p of x equals the sum of all overall y of p of x given y times p of y. which is basically the very same as this over here, P of x equals the sum of overall y of P of x and y. And you might now argue what that actually means. If you think about this as a two-variable, this is basically, if you write this down, right, then say if you think about binary variables x and y, right, you can basically specify those quantities by a two-dimensional table. And this would be, for example, in a two-valued case, you would have a table of for example, for x and y, you would have basically true, false, and true, false. Right? And this gives you a table with 4 entries. Right? And in this, you would now need to specify those 4 quantities in order to completely, entirely describe P of x and y. For all cases that you might have. You could now take the values, but you can also say, like, this is just A, B, C, and D. With the property that they all sum up to 1. So sum of A, B, C, and D is 1. And if you're now interested in the probability that x is true, right, this one over here, so how do you calculate that? A plus B. You basically take that row over here, right? And there you sum over both cases of y and take those corresponding entries from the table. This is basically what this law of total probability says, or this marginalization. You could even think about P of y being false. What is that? B plus D, right? You go with, that's summing over all x, right? P of y equals false, and these x values, right? The corresponding the two values of x. So this is basically what is behind this marginalization rule. The very same holds for the continuous case, which is a nice part, but in discrete case, the discrete case is way easier to understand. And this, the law of total probability is nothing else but replacing this with a definition of conditional probability, like P of x and y is P of x given y times P of y. Just the definition, nothing more. Yeah? This one over here. Looks magic when you see it for the first time, but this is actually, there's nothing complicated behind this. And this over here is just applying the definition of the conditional probability to that equation over here. Okay? Still there, no magic, right? Believe me, this is all not magic. Right? This is actually really relatively simple. And from that, you now can directly derive Bayes' rule, which is one of the most important equation or basic equation for probabilistic reasoning. Like if you write this down, P of x and y, conjunction in logic is symmetric, meaning that P of x or A and B is the very same as B and A. It's kind of like commutative, right? Commutativity is that. So basically, meaning if you write it down like this, P of x and y is P of x given y times P of y, just by definition. If we swap y and x, which is the same expression, right, then this is P of y given x times P of x. Yeah? And as P of x and y is the very same of P of y and x, we arrive at that equation over here. And once we have this right-hand side part, all we need to do is divide it by P of y under the assumption that P of y is non-zero. Then we arrive at P of x given y is P of y given x times P of x divided by P of y. Does nothing else but follow just from this definition of conditional probability. And these terms over here have specific names. The left-hand side part is the likelihood. This is the prior. It's called the prior simply because here this is called the posterior, simply because we are interested in the probability of x given we accumulated or information y arrived. So this is kind of like what is the outcome of that information, or how does the information y change our belief about x? And here we have no y available. So here we put in the term, what is the probability? Simply the prior value of the probability of x. Right? And P of y down here is simply called the evidence. Actually, it's symmetric to that, but it's just for being able to distinguish the two. Like one basically calls this the prior and this down here the evidence. This is actually Bayes' rule. There is one argument that will come up a couple of times in here. So the interesting point is, the interesting aspect of this equation is that this helps us to determine the probability of the state x, given we know we have the information about that y is true, for example. And in this equation, this y down here is, appears over here, and what we can see is that this term is basically independent of x. There's no x in there. And what one can now do is one can actually create an inference about that one in practice doesn't need to know this evidence down here. In order to, for example, it is sufficient if we only have y given x and p of x, if we have those two values, right, for all combinations of x and y, and all x, in order to calculate the evidence down here. And this basically follows from the fact that if we think about this term over here, which basically says it's independent of x, right? So basically it's a constant. It's the very same for every x. You can make an inference about how big this constant actually should be. And simply because of the fact that if you look at the left-hand side term, if we sum overall x and calculate p of x given, and take the values of p of x given y, what would be the outcome? Right, if you look at this equation over here, or this term, you're going to turn this into an equation. Sum overall x, p of x given y. Okay, we're going to make it easier. Like, let's look at the easier part. Sum over x, p of x. What is that? 1. Right? Now let's assume that someone provides us with some evidence. And we are now interested in what is the probability overall x, p of x, given this evidence. Any intuition? P of y. That's actually not true.
Not y, but P of the y that's given. The given y.
Yeah, this.
That the given y appears.
Pardon?
The probability that the given y appears in this.
No, I mean, the point is that someone told us y. From that we get an updated value, some sort of a quantity that tells us what is the probability of x. Like, let's think about this, the simple example, right? We look outside the window, we see someone walking with an umbrella out there. Right? We now ask the question, what is the probability that it is raining given we see someone with an umbrella? And what this equation tells us is, what this term says is, you need to sum up over both cases, right? So what is the probability that it is raining outside, given we see someone with an umbrella, plus the probability that it is not raining outside, given we see someone with an umbrella?
1.
It's 1. So this basically doesn't change anything, right, in this equation. So basically we have the situation that it doesn't change anything regarding this, we call this constraint. Right? The probability overall x, given we know something, actually stays 1. Whenever you have a probability distribution, right, the sum over all cases is always 1. even when you add, that's what we call background over here. And this is, I know that in this course it's often super confusing for students, but maybe with this umbrella example you can see that this is actually, or you get a slight intuition that this y, the fact that we know y doesn't change this constraint. That the overall x, independently of what evidence we accumulate, overall x, the probabilities always sum up to 1. You should not confuse this with this term. Right. This is not 1. Yeah. Not necessarily. Yeah. But this one is always 1. And now, given we know this, right, given we know that the sum overall x is 1, of p of x and y is 1, right, this exactly tells us what the quantity of p of y should be. If we know all the cases of y given x and x. Right? Because if we sum them up, ignoring p of y, which is the same for all x, we in fact will, with high likelihood, will get a sum that is different from 1. Right? And this p of y does nothing else but acting as a constant that makes sure that this left-hand side, because it's the same for every x, it's independent of x. So this constant cannot do anything else but making sure that the left-hand side sums up to 1 over all x. So if we don't know this, right, if for some reason we have no means for calculating this, or nobody told us what p of y would be, we can still infer what p of y is simply by calculating the sum over all these cases, right? So basically what we need to do is calculate, sorry for doing this here, p of y given x times p of x, and we sum over all x. Right? These are the values that we maybe get from whatsoever, modeling, the way we model the things. And if we calculate this, this is going to give us a sum which is likely different from 1. Huh?
Yeah.
This is, and can you make an inference? What?
P of y.
It's not exactly, it's 1 divided by p of. Is it p of y? Maybe you're right. Let's see. We are going to go to the next slide. I talked so much that my brain is actually, I cannot like do the calculation in parallel. But you look at it, we'll see it on the next slide. It's here, right? This is basically the constant is like the, yeah, it's p of y. You see? You're right. Great. You'll get an ice cream from me once we meet in Mensa. Okay, it's actually, so this is basically that what, and also this is, it also follows from the law of total probability. Right? If we look at this again, like the law of total probability, it's over here. The only difference is that we now like swap x and y. Right? It's just text replacement. So we needed this entire hour-long discussion to basically just do this text replacement. But the motivation is that the argument here is that, and this is what is typically confusing, that we do not need this p of y. We do not need to have the evidence. And we can easily replace this by this constant over here. And if we just calculate, have all the values available, p of y given x and p of x, we can calculate this constant from that. And the algorithm that we are going to use is usually like this over here. We are basically summing up all these quantities. Then eta is 1 divided by this auxiliary variable, and then we are going to multiply this with this constant with the individual values, and in this way obtain the exact values for every x. We will see this in one of the algorithms. It's not super necessary to understand this right now, but it will appear later on, actually, in one of the cases. And this is why in many cases we are going to do that what we call normalization, making sure that the probabilities sum up to 1 over all x. So there's going to be a normalization step in some algorithms, which exactly allows us to, or frees us from the knowledge of the evidence, which is sometimes hard to calculate, and we will see this in the derivation as well, and then you basically get and apply this scheme over here. Not needed right now, just as a motivation. An additional equation is this over here, which is that is important, is Bayes' rule with background knowledge. We are not going to derive this, but if you think about this equation over here, take a careful look at this one over here. All right. Here we basically and compare this with this one over here. Right? So basically, this says like the sum overall x, p of x equals 1. And this doesn't change if we add information. So the sum overall x, p of x given y is also 1. And you can regard this as that some sort of background information that you can add to that equation over here. Right? We basically write, we do have additional information, but this doesn't change the basic concept, namely that sum equals to 1. And this is also an important mechanism that basically every equation that you have can be extended by background information. Right? So you can add to virtually every equation like a bar, right? And basically add something. Right? Then doesn't change that equation. And the very same holds also for Bayes' rule. And it is actually a nice exercise to derive this. And for those of you who are interested in playing around with this, you can actually show that this equation holds, which is exactly Bayes' rule. It only differs by the fact that we add some additional information on the right-hand side. So it's p of x given y and z. Z is the very same as p of y given x and z times p of x given z. So we basically add this bar z to the right-hand side divided by p of y given z. It's basically, so for those of you who are interested in it, it's actually a relatively nice exercise calculating this. It basically says that Bayes' rule also holds when you actually add additional information. Basically doesn't change something about x and y, about this general behavior. You can simply explicitly add whatever you want as background. We're not going to prove that, but it's going to be super useful in the rest. And I think now we're going to make a short break, 7 minutes, let some fresh air in, and then continue. Go ahead. So, we'll also now talk about this background information in the context of conditional probabilities. And for example, like you can see from this here, also that you can simply add like background information to every equation that is available. It's basically the very same. So we have like p of x and y is p of x times p of y given z equivalently if the two are independent, which basically is the very same. You can also drop y when x and y are independent, even if you have background information z. This doesn't necessarily mean that when you have this information over here, that p of x and y are also conditionally independent. So it could be that knowledge about z actually introduces independency between x and y. So that's something that you need to take into account, and you need to very carefully think about these independence assumptions or independencies or dependencies. And it could be that p of x and y given z are independent, whereas they are not independent without the information about Z. So this is something that we will see also when it comes to that, we will actually make a proper statement about this. But this is something that one always needs to take into account, and these independence assumptions are usually made for simplifying things, particularly when you have, like this here is a joint distribution, and joint distributions, you will discuss this in detail in the AI course. These joint distributions have the problem that the size or the space that you need to represent those, right? We saw a two-dimensional distribution before, and this is actually a two-dimensional table. And for an n-dimensional table, you would actually need, or for an n-dimensional distribution, you need an n-dimensional table, which means that the space that you need to represent this table depends exponentially on the dimension of your, or the number of variables that you have. You could also think about this being x just being an n-dimensional state vector or an n-dimensional vector, and having a probability distribution over an n-dimensional vector means that you need space that is exponential in n. And this is particularly problematic, even on nowadays computers, because whatever is exponential is actually something that relatively quickly grows out of bounds for computers that we can ever imagine to build. And this is why one often is interested in breaking joint distributions into individual distributions, meaning that you can write down in the ideal case, like separating this into two one-dimensional distributions, which actually saves a lot in terms of memory and also computation. And the more common case is that we make this assumption over here, and we will see one particular example of this in just a few seconds, where we can actually make the assumption that x and y are independent given z, but without z, x and y are not independent. We will see this in a few moments. But this basically then helps us to make efficient calculations for this probabilistic type of reasoning. And in practice, there's always called an independence assumption, and whenever you make this argument, then you need to actually carefully argue that this independence is actually given. And if you cannot argue about this, then what you will end up with is an equation that is a suboptimal description of what is going on, and you will probably also obtain suboptimal results in your reasoning process. What we're going to discuss today is a very, very simplistic situation. We have a robot standing in front of a door or doorway, and that what the robot needs to reason about is as to whether the door is open or closed. And let's assume the robot has some type of sensor that allows it to infer, like per perception, for one single measurement, like what is the probability that the door is open. And as a robot lives in a non-deterministic world with respect to its sensors, right, it could be that in some case the robot actually, the sensor fires in a way that it says, oh, I think the door is open, and in another case the sensor basically reports that the door is closed even though it is open. So there might be errors in that, and what we are interested in now is basically making that reasoning. So they are basically iterating over measurements, that if like one measurement doesn't provide you with enough evidence, or the risk for you is still too high, then that what you can do is obtain multiple measurements. So if you want to know if a piece of furniture fits into your kitchen, and you measure it once, right, and you think, oh, that might be tight, then you maybe go there again and measure again. And then from that you basically start inferring as to whether or not that system, or that let's say dishwasher is going to fit into that part of your kitchen. So you basically want to make sure that you do not spend your money and in the end obtain an object that doesn't fit into your kitchen. So that's what people typically do. They measure multiple times until confidence is high enough to make a proper decision. In practice, we can now use Bayes' rule for calculating one or flipping the conditional part of the equations, if you remember correctly. Like, so what we are, let's first look at this problem. In this robot, we are typically interested in the probability that the door is open given the observation. And in fact, what this, what the problem with this probability or with this term is that it somehow, it probably depends on the room the robot is standing in front of. For example, students might say, okay, the doors in the student lab are more often open simply because students are more often in the office, right? And whereas the professor's room, right, is mostly closed simply because the professor's never there. Right? So, and that means that this robot that needs to make this inference actually needs to know in front of which door the robot is standing. Right? Which means that you need to assess this quantity for a single measurement independence of, or depending on every individual door. Right? Student rooms are more often open than professor rooms. Right, so the other part, like if you look at the other way of that, like P of Z given open, that equation has the advantage that it is independent of the particular room if all the doors are the same, and let's assume that also they are like have the same colors, and if you think about cameras or reflection values, if you think about sound-based like sensors, like ultrasounds, so let's assume that they are basically physically identical, apart from the fact that one room is professor's room and the other one is a student's room. Which means that like this process over here basically provides you with the probability that you obtain a particular measurement given the door is open. And this obviously is independent of which door that is, given all the doors are the same. Yeah? And this is why this is actually sometimes more complicated to assess, because you have to calculate this for every door individually, right? If the behavior of the people is different. It could even be someone who doesn't like open doors, and you know that this is a person who never has his door or her door open, then this probability would be different, right? On the other hand, like this one over here is independent of the door. Right? It just describes the physical properties of the sensor, and this is why one often calls this one causal and the other one diagnostic. It's not always the case, but in principle, one can argue that this part over here is easier to obtain and more effective to obtain. And now, the advantage now is that we are interested in this over here, right? And this is a term, we could actually learn this from data. We will discuss this as well. But in principle, this is easier to obtain because it's independent of the door in many cases. And the nice aspect now is, or the nice feature now is that Bayes' rule allows us to convert or to calculate one out of the other. Because like, Bayes' rule contains both terms here. And it's basically nothing else but that the probability of the door is open given the measurement is the probability that we get this measurement given the open door times, and this is the professor versus the student, right? It's basically the prior that like which makes like the distinction between this measurement, this term and this term over here. It's exactly this prior about how often is the door open or not, divided by P of Z, the evidence. And we know that we don't need this. And this is nice because otherwise you also would need to have a distribution about how often do I get a specific measurement. You can basically throw this away. Right? And this is basically all you need in order to, like once you have this, P of Z given open. And the nice aspect is you can easily obtain this by simply putting your sensor in front of the door, opening the door, and then calculating statistics over all potential measurements that you get, usually with approximations, but that's what you do. You put it in front of one of the doors, right, and calculate the statistics how often you get every measurement that the sensor can actually obtain. You need to do some smoothing there to avoid that what is called overfitting, something that we are going to discuss also in this course. But once you have this distribution, all you need to do is also count how often the individual door is open or not. Right? You measure like 100,000 times, or how often you want to do this, and basically get the statistics. Right? And once you have this, you can calculate the probability that the door is open given that specific measurement. Right? So let's go back. So basically everything is nothing else but counting. Right? In this case, you count how often you get a specific measurement given the door is open. You also need to count how often the door is open. Right? And from that, you get this diagnostic information. What's the probability that the door is open given that particular measurement? Right? And here, let's assume this is what you obtained from your measurements. P of z given open is 0.6. Right? So this is like how often you get this particular measurement. You could even discretize your measurements if you have a distance sensor and ask like, how often do I get something that is below 3 meters, and how often do I get something that's below, but it's beyond or it's 3 meters or more, for example. Right? This would be just like two quantities that you need, and they might be sufficient like in order to make that distinction. And then like this would be the two, like P of z given open is 0.6 and P of z given closed is 0.3. Right? And we know like if you have no other information about the state of the door, let's assume this is uniform, like both states of the door have 0.5, then we do not need to do anything else but P of open given z equals P of z given open times P of open. And we know that P of y is the sum over all these cases up there, which is P of z given open times P of open plus P of z given closed times P of closed. And all we need to do is, and this is exactly this what happens in the normalization part, right? This is P of y, which is P of z. And in our case, if you go back to this equation over here, P of z, you see P of z over here, and P of z is the sum over all both states of the door of P of z given that state times the prior of that probability of that state. Yeah?
In the next one, the probability of zeta given open and the probability of zeta given not open shouldn't be 1?
No, it's not. It's just typically less than 1 because you have 4 cases, right? And it doesn't necessarily need to be 1 because it needs to be 1 over both cases of all cases of z. So usually it's the very same that we had, similar to what we had before. It's also pretty confusing usually, but P of z, the sum of all y, P of z given y, is not necessarily 1. The other thing is P of x is sum of all z, P of z given y, this is 1. The other is not usually not true. And if you assume those quantities, then all you need to do is just fill in the values, and then you obtain like P of like 0.67. And if you compare this to the prior, that the prior says, okay, we had a like uniform prior, like both cases have the same probability. We are now in a situation that the probability that the door is open is actually higher than before. So this measurement somehow increased the probability that the door is open. Right? Okay, as I mentioned, like in practice, we want to measure more often. And now comes this a little bit more complicated part. Right. Let's assume the robot obtains another measurement, Z2. Right. What can we do with this new information then? Or in general, we could ask the question, let's assume we have n measurements, and we want to know what is the state of the door given n measurements. This is a general case. Derivation. And now we are going to make a trick, and we are going to make, but all this looks super complicated, but it's just textual replacement. So what we're going to use is this Bayes rule with background information. Like, for example, like if we do P of A given B equals P of B given A times P of A divided by P of B. Right? Bayes' rule with background information is P of A given B and C equals P of B given A and C times P of A given C divided by P of B given C. Okay? It's nothing else but adding C to every term that we have. Okay, but this is all you need to know. It looks super complicated, but it's actually behind this is just a textual replacement trick. Recursive Bayes updating. We are interested in estimating the state of the door given n measurements. P of x given z1 to zn, z1 to zn. And what we are now going to do is this part over here is a sequence of measurements. And the replacement I ask you to do is nothing else but, like in this equation, A equals x, B equals, in this case, let me see, Zn, and C equals Z1 to Zn minus 1. Correct? Any doubts? This is it. Huh? Super trivial. There's actually, it's a no-brainer, one says. Huh? When you see this equation, you think, oh my goodness, but it's actually Bayes' rule with background information and just this very, very simplistic replacement trick. Huh? And this is very, very often the case in this probabilistic reasoning. So these equations look magic, and there's actually just definitions and textual replacements. Okay, this is, we are now like in this, we do have these equations over here, and we are now going to do like, to make a reasoning about this term over here. Right? So what we see there is the probability of the nth measurement given we know the state of the door, right? And all the previous measurements. Right? And if you think about, for example, a camera, or let's say a sound-based sensor, right? So you emit a sound cone and measure, like, get this measurement, Zn, right? And let's assume you have waited for an hour until, like, the echo is completely gone, right? So there's actually no chance that you will actually, the echo from any former sensation will actually get back into your receiver, right? And given, the argument now is that given the state of the door, given you exactly know, for example, that the door is open, right? This is the assumption, right? The argument is that Zn is independent of all previous measurements. If you think about this ultrasound, it emits a sound, right? And given the state of the door, right, the state of the door influences the measurement. It depends on, like, when it's closed, it might be different from when it's open. Right? But once we know the state of the door, like, it gets independent of all previous measurements. Actually, this is not the case when we do not know the state of the door. Simply because, like, in a normal situation, like, the measurements are somehow correlated in the sense that you would assume that if you don't move and if you don't change the world, the next measurement is relatively similar to that what you have seen before. So if I tell you that n minus 1 and tell you, oh, it was less than 3 meters, then you would probably argue that, okay, the next one is more likely to be less than 3 meters than more than 3 meters or more. So this is basically the argument that if we know x, right, then actually the state is going to be, the observation is independent from the previous ones. If we don't know x, then it's actually not the case. Basically, the knowledge of X reduces this perception problem to the purely physical behavior of that sensor. The information about the state of the door encapsulates basically all, or entails, or contains all the information that of the previous measurements. So basically, this is one assumption that one typically does. If you are not happy with this, or if you don't live in a world where this is true, then you cannot make this assumption. And this is typically called a Markov assumption, saying that Zn is independent of all previous measurements if we know X. If we don't know X, then this is actually not the case. And that means basically that Zn1 to Zn minus 1 do not provide us with any information about Zn, given we know the state of the door. So which means that we can actually drop those terms from this equation, and we end up with P of Zn given X. And then we have this term over here, P of X given Zn to 1 to Zn minus 1, and this evidence down here, which is like an n-dimensional term, which actually is exactly the problematic case that we do not know, and it's extremely hard to model, namely the probability of Zn given Z1 to Zn minus 1, without knowing the state of the door. Basically, the dependency of these measurements without additional information. But fortunately, we have this constraint that the left-hand side needs to sum up to 1 over all X. So we can replace this term by this constant over here, which just makes sure that the left-hand side sums up to 1. We basically can drop this term down here, and we end up with this equation, eta times P of Zn given X, times this prior over here, which is X given Z1 to Zn minus 1. And every computer scientist now immediately sees a recursion over here. Because what we basically have, we were interested in estimating the probability of X given Z1 to Zn minus 1. We reduce this to the problem of calculating the likelihood of the nth measurement given X, and have to multiply this with the probability of X given Z1 to Zn minus 1. So we basically reduce the problem size by 1, which is a recursion. The next step that we do is we basically apply this argument recursively, because structurally this is identical to this one over here. It's the very same thing. We take as background knowledge Z1 to Zn minus 2, very same argument, right, which makes us in the end ending up with a constant that is a product of n normalization constants. And we have this product overall from I to n over the likelihoods of this observation times given X times the probability of X, a prior probability. Meaning that we can actually replace this term over here, which is a high dimensional probability distribution, by the product of n two-dimensional probability distributions.
How exactly do we choose the constants?
This is done by you looking at, as I mentioned before, you basically sum up all these values, overall X, and then this is basically the 1 divided, and you divide the entire every term by this sum. Right, so this eta 1 to n is basically 1 divided by the sum of all those quantities here, summed over all X. You see this in, for example, it's the very same as in here. Like we basically take this value plus the opposite one. For both cases, this is X. Right? We have X equals open, X equals closed. And we get this also for closed. Right? We would basically calculate the very same for closed. And the denominator stays the same. You take both these nominators, sum them up, and then this gives you basically the sum. We'll see this just also in a second. But this is also called recursive Bayesian updating, or like the posterior estimation, where this prior also is contained. So we have a second measurement now, right? So we basically can actually serialize this entirely and have P of Z2 given open and P of Z2 given closed. And then we can now calculate what's the probability. Oh, we use this as a prior, like 2 divided by 3. That was the old quantity. And then we do the very same as before, just having Z1 and Z2 with this as prior, and then we obtain like these quantities over here. It's just like entering like 2 divided by 3 into here. Like this is the P of Z2 given, this is P of Z2 given open over here, and then it's basically the sum of the two in here, and this is like the outcome of the entire calculation then. So in this case, that means that the second measurement actually reduces the probability that the door is open. So this is basically the idea how this is done. And recursively, like you only need to do, like if you look in an implementation point of view, you can go completely incrementally there. I mean, all you need to do is basically always only consider these equations over here, or the denominator over here, which is calculated by this normalization process, which is also in this equation. Let me see. This, oh no, sorry, this basically is the way you calculate this. This was the description of how to calculate this denominator. It is basically, you see that this is actually the sum over those terms over here, and we spelled this out in this equation or in this example with the door opening. So this is basically this, where you see exactly this auxiliary is the sum over all these auxiliary values. Right, and same down here in this example, where we actually calculated this this sum. Like you see here, this is 1 divided by 4 plus 2 times 2 divided by 3, and this is the other quantities for the closed case. Right, so for those two basically over here. And all you need to do is basically do this so this term over here is this one, and the left-hand side is this one over here. And in here you basically put the old priors, which is now in the case that you have a second measurement, the posterior of the former round. That's basically what you need to do there. So at the end today, we also want to incorporate actions, and actions are needed because, or in the incorporation, because the robot might move, right? And when it comes to position estimation, or it might even use its arm to open the door. And the question is, how can we deal with that? Like if things or systems actually have actions to control them. Actions, we know, are never carried out with absolute certainty, and typically actions increase uncertainty. There are a few cases where it can also decrease uncertainty using actions, but in practice, in most cases, they actually increase uncertainty. So in our the probabilistic reasoning term, we are basically interested in a type of equations like this. This is what we assume to be given. Basically, what it says is a distribution about how the world changes given an action. So if you think about this door opening example, that the situation that we are faced with is we do have the robot standing in front of the door. We know the state of the door, right? So let's assume the door is closed. The robot performs an action, pre-programmed action, in the most simplest case, which is trying to open the door. And what this statistic basically says then is, how often does the robot succeed in doing so? So basically it says, what is the probability that the door is open, given the door was closed before, and the robot executed its door opening action? There's also very, usually you can describe this by relatively simple distributions. We will see this as some sort of in this example, as a stochastic finite state automaton. It's basically this what it is. All right, so it basically specifies the probability that the world changes in a corresponding way after executing action U. Right, so this is the closing door example, right? And we are interested now in this opposite problem, like what is the probability that the door is closed given it was open before and the robot executed its door closing action. But we can also ask the question, what is the probability that the door is closed given the door it was closed before and the robot executed that action. Right? And you can, for example, specify this then entirely by a graph like this. Right? So if you think about here that probability that the door is closed given it executed a closed door action, it's always one, it never changes. Right? So you're lucky it doesn't introduce noise. It never goes from closed to open with the closing door action once it is closed, but if it's open and it executes a closed door action, and in 90% of all cases the robot actually succeeds, and in 10% of all the cases that the robot actually fails, which means that we have a stochastic graph of that type. So the closing door action is successful in 90% of all cases. So in practice, we are now interested in, we have the robot standing in front of the door, right? And we do not know the exact state of the door. This is what we don't have, but we have this distribution over here. We have done plenty of experiments, confirm, and we got these values, right, from the experiments. And the situation now is that the robot stands in front of the door, the state of which is not exactly clear. What we maybe have is a probability distribution that tells us what is the probability that the door is open or closed, but we do not have the exact state. Right? So this term over here is actually never known to a robot. Right? The robot never knows what the exact state of the door is. But we know that it makes sense that this is somewhat easy to obtain. Right? We just put the robot in front of that door, takes the door into two states, and then let the robot operate in the corresponding way. And then we do nothing else but counting. So we can assume that we have this probability. Unfortunately, right now, it doesn't help us because the robot never exactly knows as to whether the door is open or closed. But what we are interested in is like the state of the door given that action, and without exactly knowing what the state of the door was. And here now comes this law of total probability, which basically says this is nothing else but, let's say, take the discrete case, but summing over all x prime and p of x prime and u times the prior of x prime. And in here, so it's basically nothing else but the equation of conditional probability, in this case with background knowledge. It's basically p of x equals sum over y, p of x given y times p of y. Right? If you calculate this with background information, let's say take p of x given z equals sum over y, p of x given z and y times p of y given z. Textual replacement in here, x stays the same, z equals u, right? And then this is what we obtain, right? We simply replace, and x prime equals y. Nothing else but text replacement again. The interesting aspect now is, let's assume like that this is what we did. We executed. We are interested in the state of the door being x, and the action u having been executed by the robot. From this law of total probability, with background knowledge, we can actually infer this over here, that this is exactly the sum overall x prime, like p of x given u and x prime times p of x prime given u. Turns out that x prime was the state of the door before we executed that action. Right, so x prime actually happened before, or it was like the state of the world before the robot started to control its arm. Which means that it's actually independent of that, right? So the robot cannot change the past, as we also cannot do. Meaning that the probability of the prior state of the door is independent of the action that we executed. The robot should know x prime, and therefore it chose its action u independent of that x prime. Which means that x prime is actually independent of u. Which means, on the other hand, that we can actually get rid of this u over there. And now we are in this comfortable situation that we have a term over here, p of x given u and x prime, and just need to multiply it that we have already, for which we have statistics. And we can use p of x prime, which is a state of the door without any information. And the belief about that. It's just the prior state of the door, right? Which means that we can now do exactly this over here, and then in this way reduce this to terms that we actually know. And if you look at this, like for the closing example, so the probability that the door is closed, right, given we executed a closed door action, right, is p of closed given u and x prime times p of x prime, prior state of the door, right? So it would be about both cases of the door, p of being closed given u and the door was open before times p of open plus p of closed given u and closed or not open times p of not open. And if you just, and these are all quantities we have, right? This is the priors that we got from our perception system. It was 5 divided by 8 as far as I remember. And this was its 0.6 what something. And this, we know that the closed door action succeeds in 90% of all cases when it's open, which means that we actually get this and we end up with having 15 divided by 16. Just for the sake of like completeness, we can also calculate the probability that the door is open after that action, and then we just need to like enter the specific terms over here, and then we end up with a quantity that is 1 divided by 16, which is nice because these are the two potential states, and the sum overall over both states of the probability of the state of the door needs to be 1. Right, and just to give you an idea about what's going to happen on Friday, what we're going to do then is we're going to generalize this and derive a general equation. And we're basically looking at, we're doing the very same thing as you saw today, right? We're going to do this entirely on the blackboard on Friday, and we're going to be done in 45 minutes on Friday. The general assumption here is, or the general idea is that we like have a stream of data, controls and observations. Right, so the robot operates the door and measures it. We do have that what we call the sensor model, which is this one term p of z given x, right? The probability that the sensor provides us with a specific information given this particular state of the system. And we do have that what we call an action model, which is p of x given u and x prime. It's basically like specifies how the world changes when we execute a particular action. And we assume that there is a prior about the state of the system, which if you have no information, it's a uniform distribution over all potential values of the state variable. Right? So in general, what we're interested in is estimating the posterior about the state of the system at time t, which is p of xt, given all the controls that we executed and all the measurements that we had. So you can, for example, consider this as a problem of a robot navigating around, having a map of the environment and using its sensors to actually measure distances to objects. and moving around, which are controls. And what the robot now wants to know at every point in time, where am I, given I executed this particular movement and obtained this particular measurement. And this over time, meaning I executed t movements, and at every point and after every movement I observed this particular measurement. So where am I now? This is one of the prompts. And we call this a probabilistic belief about the state of the system at time t. If you want to, I can quickly show you the entire equation to get an idea what is going to happen. Are you curious or afraid? We will have a look at it on Friday. Right? So thanks for coming today, and see you on Friday, and enjoy the nice weather today and the rest of the day.